Yeah, so those of you looking for answers to the daily Q, the first one should have been 3.49. The second, and that's in what's the units on angular velocity?
Radians per second.
Radians per second. And then the second one should have been 1.05-ish, and that would be in what units?
Meters per second.
Meters per second, provided you changed your radius to meters. Okay. All right, so we're going to talk centripetal acceleration a little bit. Since velocity is constantly changing direction, but maybe not value, there's always going to be an associated acceleration with any rotational object. So remember that when we talk about vector quantities, like velocity and acceleration, that we talk about both direction and magnitude. If one of them is changing, then it's a vector quantity. So when it comes to rotation, there's always going to be an acceleration associated. And for centripetal acceleration, specifically, we're going to see how this affects and what direction it points when you are the thing in the object that is rotating, okay? Specifically, we're going to see one here in a second, but we see it's going to be something that is showing a moving object in a circular path. And the object is moving at constant speed, so that's one of the major things you need to know. The second is going to be, acceleration is going to be the direction of the change in velocity, okay? When it comes to a rotating object, if the velocity is constantly going like this, the change in velocity is going to be pointing inward. So towards the center of your rotating object. We're going to see that here in a second. And we're going to see the centripetal acceleration is going to be denoted as A sub c. Centripetal means center seeking. It's like a language root. So when you think about centripetal acceleration, think it must be pointing towards the center. I'm going to show you the picture here in a second. But I wanted to explain the picture before you saw the picture. So here we are. Our centripetal acceleration points towards the middle always. Okay? If that is the case, how do we figure out the magnitude? How have we figured out the magnitude of acceleration before? What was the formula? Does anyone remember? Change in velocity over time, right? So what's our version of velocity in the rotational sense?
W?
W, right? V and W are analogs of each other. If that's the case, then A sub c is probably going to have something to do with a changing velocity, angular velocity specifically, over time. They talk about how they derive it. In particular, the case for centripetal acceleration, since we're still talking about a centripetal meaning linear version, what they actually end up doing is this. So they derive a different way, but they put it in terms of linear velocity. Now, how do we get from linear to angular? Does anybody remember from yesterday? What's the equation?
Isn't it W over
R times W. Okay? So if we want to derive this in terms of W, what are we going to do? That. So then what happens? We get R squared times W squared over R. When R cancels, and A sub c can now be written, times R, in the angular sense. Weird. Very weird. But remember, we're not actually dealing with the angular acceleration quite yet. We're still dealing in linear accelerations. I think that's exactly what they're going to do next. One of the things to note about this centripetal acceleration is that the faster you're going, the more you're going to feel it. So the higher the number is going to be, especially since we know that velocity, as it changes, is going to be squared. So the faster you go, the more you're going to feel it. And one of the things you can use to think about this. Anybody ever been on that thing that spins at like a carnival? Spins really, really fast and you like move up and down and you can't like move your hands again. Yeah. The idea is that centripetal acceleration is the thing that's making you spin and feel that way. Okay? We talk a little bit later about about the observer's frame of reference again. Whereas right now, it's hard to kind of experience centripetal acceleration in any meaningful way because you can only go so fast. The closest to centripetal acceleration that I can explain to you is if you take a banked curve really fast, you kind of feel yourself like pulled towards the outside of it. That is that whole idea behind your velocity is changing very quickly. And so is the direction of your velocity when you take a curve really fast. And so you feel that pull. That pull is you resisting that change. And that pull is kind of the thing that we describe acceleration with. Okay? A lot of times we also say that that's gravity. Obviously, you're feeling the change of gravity, the shift in gravity. But for us, if you're not being pulled downward, you can't really talk gravity. Right? If we're being pulled in a direction that is parallel to the ground, you can't say, oh, gravity's pulling me outside of the curve, right? Think about taking a curve really, really fast. Do you get pulled down? No, you get pulled out. Mm-hmm. So that force is what we call a fictitious force, and we're going to talk a little bit about fictitious forces. But from your perspective, you're feeling this pull, and that pull is only really being created by the change in velocity. Really odd concepts coming at us in this chapter. Okay, from there, an example of something that has the ability to use this constantly changing velocity is going to be a centrifuge. The idea behind a centrifuge is that if we spin something really, really fast, that it'll separate by density. The heavier object will be on the outside, and the lighter object will stay towards the inside. This is something that's going to take advantage of both centripetal acceleration and gravity to achieve a goal. So who's seen a centrifuge before? Anybody? I know I have some in here. But what they're these angled circular devices. And so you put a tube in, and the tube kind of sits on an angle, right? And that angle exploits both the centripetal acceleration that spins really, really fast, and since it's pointing downward, gravity, right? So the heavy stuff kind of settles towards the bottom, and the lighter stuff stays toward the top of it. Okay, so let's do a problem. You're given some information about the magnitude of an acceleration of a car. What is the acceleration due to gravity for this gentle curve, aka how many G's is this person pulling? You're also given some information about a centrifuge. So we want to know what the centripetal acceleration is. We have a couple of formulas we can use to do it. We have a value for velocity, right?
Yeah.
In our case, we have a radius of 500 meters. Do we need to convert that?
No.
No. Our velocity is 25. So what is our centripetal acceleration? Calculator. Oops, meters per second squared, right? Do you agree?
Mm-hmm.
Okay. And then it says how many G's? Do you remember being asked how many G's before?
Yeah, but I don't know what it means. I forgot.
So we always want to take some number of acceleration. In this case, we're going to do our centripetal acceleration, and we want to divide it by the value of gravity.
So the G stands for gravity.
Yeah, so how many, so have you ever heard like someone say, oh, they're pulling 6 G's
Oh, yeah.
in a plane before, or 4 G's or whatever it is? Those are all magnitudes of how many gravitational forces they're pulling. Human beings pass out at I think it's 5 G's of force. So pilots that go really, really fast in those jet planes have to learn to withstand the effects of intense changes. It's kind of cool. Say again? AC. Sorry. AC. So what's the value in G's, if you will?
0.127.
So we're not even pulling a G when you take a curve at 25 meters per second. Okay, now next one says calculate the centripetal acceleration of a point, 7.5 centimeters from the axis. This is a fancy term for what? Radius. And you're given the spinning revolution. So this is in revolutions per minute. This is pretty close to an angular velocity, correct? How do we get this into a linear velocity so that we can do this? So we're going to go revolutions per minute to radians per second to meters per second. How do we go from radians per second to meters per second? This is part of your daily Q.
R times W?
R, W. Get used to some of these formulas. You're going to have to do convergence. A lot of times when we see rotations, we're given how many rotations per minute, or we're given revolutions per minute, or we're given radians per second. We want to always be able to get into the other one if we have to. Okay, so do that problem. You got this. The second part just has to divide it by 9.81 again. Tell me how many G's. Who's their angular velocity in radians per second?
I got a big number.
That is a big number, so that makes sense. What'd you get?
I got 7,853.98.
Okay.
Okay.
Centrifuges spin really, really fast. We're talking like 1,000 rotations a minute. I have one somewhere. I'll find it and plug it in for you tomorrow for fun.
Oh, it's an ultra centrifuge.
Yeah, so they spin really, really fast.
Okay.
Okay, what's next?
Do that one.
Times the radius. Don't forget to convert to meters. Should get slower. What do we get? Now we're in meters per second. Now we want AC. What'd you get?
4,626,398.7.
898?
398.7.
And that's in meters per second squared?
Oh,
Again. Huh?
It was 626, not 627.
626?
Yes.
Okay.
I did get
That's a really freaking big number. All right, next thing says to take this and compare it to gravity to see what the ratio is. So you're going to divide by 9.81, and what are you going to get?
471,600.
400?
No, 471,600.28.
A lot of G's, man. It's really, really, really fast. not only is it really fast, but it gets very fast very quickly, according to this. Okay. Let's talk centripetal force. This is the last section you read, right? Section 3?
Mm-hmm.
Okay. This is section 3. The thing didn't change until the next slide. Sorry. We're talking FC. So in the past, we've talked about net forces. Yes?
I'm sorry, quick question on the problem.
Yeah.
I understand how you got to angular motion, but why did you multiply it by the radius of 0.075? Like what?
That was the 7.5 centimeters.
Right.
Okay. To get from angular to linear, you have to multiply the angular velocity by the radius.
Oh, okay.
Yeah.
So
Can we not leave it in angular? Isn't there other formulas that W squared times R?
You could use that too. Once you have angular, you should get the same number, right?
Yeah.
Did you still get the 4 million if you did it that way?
Yeah.
Okay. I mean, we addressed it, but I mean, yeah, so you can do it that way as well. So, do you understand, Jessica?
yes.
Okay.
Thank you.
You're fine. All right, so, remember this?
Yes.
We don't like Newton's second law, but Newton's second law still applies, even when we're rotating. The angular or the rotational version of Newton's second law is going to use centripetal acceleration. One of the most common ways we're going to use this is using banked curves, and we'll talk a lot about banked curves in the future, but there aren't a lot of banked curves for us to see visually. Anybody ever, well, I guess you all probably have, gotten off at the exit 315? Yes. From the north, like coming south, getting off at exit 305. As you start to get to the exit, the whole curve, you know, it's like this huge curve. It is on an angle. We call that a banked curve.
Oh, I know
So
what
that you
you're
know, so that you have an idea of what a banked curve is. You kind of feel yourself going up, and then if you're getting off the highway, you just kind of immediately exit the banked curve. But if you continued along that curve, eventually it kind of settles back out. Okay, so the idea of a banked curve is that it kind of travels flat until you get to the curve part, then it does this, then it flattens out again. That make sense? And you can feel it when you go anywhere on the highway. Most of the times that's really where you're going to see them. You're not going to see banked curves on the roads in the country because people aren't supposed to be driving that fast on them. Those of you that do drive very fast in some of those curves in the areas of our town that are not well treated in the winter, you've probably seen people slide off the road completely because those curves are not banked to keep you on the road. So the idea behind a banked curve is if you're taking that curve at a certain speed, you don't have to slow down because it accommodates for that extra speed by kind of adding in a little bit extra like centripetal acceleration or centripetal force, if you will. Okay? It's kind of weird, but that's the physics behind why the roads are designed the way they are. All right, according to Newton's second law, we have FC. Remember we did say that V could be substituted or AC could be substituted for RW squared. So we could also get that the centripetal force equation, FC, equals this. So I want you to do what it says. It says to rearrange to solve for R. Rearrange this equation to solve for R on your own. Humor me. You get it?
I think so. Yes.
Okay, good. Okay. The reason I wanted you to rearrange it because what I want to do is I want you to see how radius and force are related to each other. If you have a large centripetal force, we're going to see a small radius of curvature. Now that is not like something you can kind of see directly because you aren't taking into account the mass and the angular acceleration. Okay, so the overall radius to force relation depends on both mass and angular velocity as well. So if you're going really fast, right, if this number is really, really large, this number gets smaller, right? That is why this says what it says. It's trying to demonstrate to you how radius is related to force. It's not just R and F are directly proportional. That is not correct because you have to take into account the rest of the equation. Okay? All right. Let's do a problem. Part A says to calculate the centripetal force, so FC, exerted on a car with a mass of 900 kilograms that negotiates a 500 meter radius curve at 25 meters per second. So our goal is FC, and we have information about R, we have M, and we have V, right? So this is going to be our centripetal force equation if we have an angular velocity. What would our centripetal force equation be if we had a linear velocity? Because that's not on the board. If AC is V squared over R, couldn't we then write that equal to FC? Do you agree?
Why?
Because AC has a linear and an angular quantity. Do
Oh.
you see that?
Oh, because V equals R.
Mhm.
Okay.
That make sense?
Yeah.
Okay. Take it for granted if you don't. If you don't see it, this is the equation we can use in this particular problem. Is this going to be easier than trying to convert something to an angular velocity?
Yeah.
Probably. That's an extra step. So there's going to be two different analogs. This will be what we call rotational, and this will be linear. And remember, the difference between rotational and linear, rotational is going to have angular velocity in radians per second. Linear is going to have linear velocity in meters per second. Your goal is FC. Yeah. It's a multiply. I just got a little overzealous in my dots. Okay. I'm gonna rewrite this. You got FC. You got FC linear. FC angular. Some of the new stuff from today. Is there anything else I missed? I don't think so. You'll notice that in section B, that equation should look familiar. What is that?
Mu. Oh, sorry.
Which is
Static friction.
static coefficient of friction. I like it.
Yes.
Did we get, how are we doing up there? So I'm guessing we use this. You're looking for FC. That's your goal. It says, what is this centripetal force? So it's this value.
Don't we just plug in numbers?
Yup.
Okay.
Just plug in chunk. Ooh, the next one gives you a free body diagram. Yes.
So everything is divided by your radius?
Yeah.
1125.
Yeah. What'd you say?
1125.
Yeah.
1125 what?
Even.
No, I know. The unit.
Oh.
It's a force. What's the
She said
unit?
even. She said even. No decimal.
Newton.
Sorry.
1125 what? Even. I mean, it's odd, but it's fine.
I'm not even good.
All right. Next thing we're asked to do is to find the static coefficient of friction between the tires and the road, which is why the car doesn't slip. Okay? We're given a free body diagram. So I'm gonna just, do we need this anymore? Okay, because I'm just gonna put this value off to the side. We do want it later. So what we are told in this free body diagram and in the subsequent equation underneath is that the force of friction is equal to the static coefficient, is equal to the centripetal force. That's the first thing we're given down here. The second thing we're given is that it's going to be equal to mu Sn. And the last piece of information that is really, really helpful is the free body diagram, which looks like this. So, how do we know what n is?
Wait.
In this particular case, isn't the normal just equal to the weight? Do you agree? We're on an unbanked curve in this particular problem, so there is no like angle that we have to deal with or anything like that. We will talk about how to deal with banked curves later, but what happens is instead of the weight pointing straight down, weight goes on an angle. When weight's on an angle, what do we have to do?
Parallel, perpendicular.
We have to use parallel and perpendicular components, and so on and so forth. So you can probably kind of visualize how that problem's going to look at this point. We're not quite there yet. Okay, so if n is equal to w, remember that w is always mg. On our quiz, some of us did not remember that w is always mg. And when you did w, for some reason this became cosine of 35 degrees. I don't know where the w went for most of you, but we forgot mg on our quiz. Like this, I don't know how this happened to all of you. We did this like, I don't know, 100 times. So, always remember that w is m times g.
Got it.
Okay? All right, so what in this case is our mg? 900 times 9.8.
$8,820.
And that's a Newton, right? Okay? So then we're told Fc equals mu Sn.
Oh, is this where we have to like look up the mu?
We're calculating mu in this problem.
Oh,
Coefficient of static friction is our goal. That's
because we
mu.
already figured out that one. Okay.
So we're going to plug in our numbers. Remember that mu's should always be less than 1.
0.128.
Nice. Okay. All right. So now let's talk about a banked curve. Again, the only change to what we've just done is our free body diagram. Everything else holds true. Can I erase this? Or are we still right now? Okay. Gonna leave our formulas. Okay. So, in case you can't see it on this diagram, the only change here to our free body diagram is that our weight ends up on an angle. So, our object is in contact with a slant. Our object in this case being a car. Remember that weight always points straight down. Okay. In this particular chapter, for some reason, it chooses to, instead of do W parallel as W, what would the angle be? Sorry. W parallel would be cosine? Opposite? Nope. Sine. Okay? So this is what we've always done, right? That looks familiar to you? They choose, for some reason, to move to here to tell you it doesn't matter what you choose. What matters is that you realize that the perpendicular direction, so the one that goes up and down, right? That's this guy, is going to equal FC. I know. I'm with you. It doesn't make sense. But this particular chapter decides to change what they're going to use on an angle. They decide that W is the thing they want to keep and N is the thing on the angle instead. Even though up until now what we've done is we've rotated the diagram to make N the thing that's always pointing up.
So can we
Does that
still
make
do
sense?
that?
You can still do that as long as you realize this is equal to FC and this is equal to your whatever's going this way. So it could be your friction. Make sense?
How did you choose for weight perpendicular
To
to cosine?
be cosine,
Yeah.
I'm looking at this triangle. So isn't cosine adjacent to the angle? Because this is my angle,
Oh,
right? Remember that whatever this angle is, theta is the same as this angle.
is there any times that that adjacent angle will be parallel? No.
Shouldn't be.
So should
Even if you flip the slant, it should be the same thing.
so weight perpendicular should always be cosine.
Yeah. I mean, well, I hesitate to tell you yes, because it really does depend on the situation.
Yeah.
If you're talking about, there are situations where it might not be, so I don't like to say that. Because that's why we got away from y and x. That's why we got away from wy and wx, because
Right.
it's not always going to be x and y. On components specifically. Now, with weight, yeah, that might always be the case.
Yeah.
But
there might be
we resist saying it will always be this particular expression, because sometimes there are situations where it might not be. We could be talking about an upside down something or other, and then all of a sudden it's flipped. And then you're going to be mad at me. So let's not say always ever in this class. Yes.
Oh, well.
I'm sorry.
My question was, is W perpendicular always going to be
That's
equal
what
to
we were
C?
just talking about.
Oh,
So
okay.
it will not always be cosine,
That
is what we're
equals
saying.
FC.
But it should
Okay.
be FC. Whatever W perpendicular should always equal FC,
Okay.
is what we're saying. We're interpreting this diagram and saying this. Woo! Doing great, guys. Okay. Next thing we want to talk about is ideal banking. So what happens when we have the ideal situation is that the force of friction will equal, the external force is going to equal whatever the centripetal force is. So in other words, in an ideal banking situation, FC equals F net, which is the assumption we've made here. Call this an ideal banked curve. When this is the case, this will equal FC, and this will equal W. So this is for ideal banking. And you would be given these equations that say, for ideal banking, I would tell you this would say ideal banking. It's useful to use these shortcuts when we're talking about ideal banked curves, and it's a very specific situation we would use these shortcuts in. So again, you would see these equations. Now, in the particular case of this, n sine theta becomes that long, this thing, right? So we replace FC with this. And this is of course all the horizontal. The vertical components of an ideal band curve are going to be n cosine of theta equals mg. So W. All we did was rewrite these two equations to include their full definitions, right? Do you see what I did? Do you understand why I did what I did? Yeah? So the idea here is if you're given a bunch of information and you're trying to find something, you have a lot of ways to approach it. Remember with kinematics, you had 5 equations and there were many approaches. You could do a multi-equation approach. You could do a single equation approach. For some of us, we may not ever see the single equation approach to problems like this. And that's okay. If you have to do multiple steps, like for instance, I decided I was going to calculate FC first, and then I went and I plugged it into n sine theta to find n. Okay? You may have done that in 2 steps, whereas there's now a 1-step way to do it. That make sense? Kind of sort of? So multiple step approaches to different problems in this class. And this is no exception. The next thing we are going to work on is incorporating all of this information into our kinematic equations. Before we get there, I think this is the last equation in this chapter, is how to calculate the angle of an ideally banked curve is this formula. This formula specifically. So this is how to calculate the angle of an ideally banked curve, assuming no friction, which is never the case. But how to calculate it. Given the information we need. Now, just like before, if I know information like W, can I do some substitutions into this little thing to get W instead of V? Absolutely. You know that V equals R times W, so could you plug in RW squared instead? 100%. Many approaches to the same problem, and that's okay. Okay. One of the things that I'd like you to do is practice this last one. It says to illustrate, calculate the speed. So V is speed, right? At which a 100-meter radius curve, so here's our R, banked at 65 degrees, should be driven if the road is frictionless. Frictionless in this case means ideal banked curve. Okay? So we can use our ideal equations that we've got over here to figure out anything we might need. It does say what is the speed. So do any of these have V in them?
Yeah.
They do. Do we have R?
Yeah.
Mm-hmm. Do we have M? No. Do we know N? The normal?
No.
Probably not. Okay, so let's think. What else can we calculate? We could theoretically get A given V and R. We don't have V. What do we think?
Where would we go once we have AC?
Can we calculate FC after finding?
Yeah, but we don't have the mass.
Oh,
do we?
yeah.
We don't have the mass.
But can we figure that out? We don't have to wait there.
Hmm? I'm gonna see.
If we figure out AC, can we do the equation below it and find out W?
Do we need W?
You have to do
Is it W? Oh wait, that's angular. I'm thinking that's weight.
Wonder if there's 2 equations, 2 unknowns.
I would say 'cause we don't have weight. do we?
No, because we don't have V. Dang it, what am I missing? Because they basically all want mass or velocity. Well, we troubleshoot tomorrow. We'll figure it out. I wonder if I'm missing a piece of information. If I am, I'll figure out what it is and I'll let you know tomorrow. What should you be working on tonight? You have a homework set. Can you start section 2? Absolutely. Pay attention to your equations, please.
Thumbs up.
Bye.